we're going to once again return to our favorite situation of 2 blocks on a ramp. I have 2 other videos up dealing with a similar problem. If you have not watched the other blocks on a ramp, usually they have the title Atwood in the machine, or in the title, because this is a modified version of an Atwood machine. If you haven't watched those yet, you may want to go do that, because I am going to talk about several parts of this fairly quickly, because they are explained at great length in the other 2 videos. There are 4 questions I want to answer about this situation, and here's what I've got. I have 2 blocks, M1 and M2, and we're going to say that M2 has a mass of 13 kilograms, and that the angle of the ramp is 36 degrees. I want to know what is the mass of M1 if the blocks are in equilibrium, so if there is no acceleration of the blocks. I've done this problem once before, so I'm going to write down the steps very quickly here. If you want the extended version, again, go watch the video. So, the forces on the blocks. This block has a force of gravity pulling it down and a force of tension holding it up. This block has force of tension pulling it this way, a normal force from the ramp this way, and force of gravity straight down. And for this block, I rotate its coordinate system so that negative x is lined up with the string and positive y is lined up with the normal force. And from that I find that the force of tension is equal to the force of gravity on this block, 1. I'm sorry, this is 2 over here. Nope, that's the way I wanted it. 1, 1, 2. That the force of tension is equal to the force of gravity on block 2, right, times sine theta. And then from that, I look over here and say, oh, well, the force of gravity on this block must be equal to the force of tension. So Fg1 equals Fg2 sine theta. And that M1g equals M2g sine theta. So I have M1 equals M2 sine theta. And then if I plug in the numbers that I know, I get M1 equals 7.6 kilograms. Again, I did that quickly. There is an extended video walking you through that problem if you want to go watch it. Now let's think about a different situation with the 2 blocks on the ramp. So I'll call this part A. In this situation, we're going to say that the mass of block 1 is 6 kilograms. The mass of block 2 is still 13 kilograms. And now I'm going to answer, if we let this thing move, what is the acceleration of the 2 blocks and which way? I also have a problem very similar to this in the videos. So if you want the extended version, you can go watch that. This will be a shortened version. Well, let's think about block 1. It only has y forces. So the sum of forces in y on block 1 is equal to the mass of block 1 times its acceleration in y. Similarly, the sum of forces in x, remember, I've made x go along the string. Sum of forces in x on block 2 will be equal to the mass of block 2 times its acceleration in x. And I'm only worried about x because that's how the string would pull. And I know that these a's are the same because the blocks are attached by a string. So they have to accelerate together unless we're allowed to, say, stretch the string. From that, what I can conclude, if I start writing out the forces, so here it's Ft minus Fg1 equals M1a, and we're just going to call them a because it's the same now. And over here, Fg2 sine theta minus Ft equals M2a. And then then I can start to solve for A by recognizing this equation is simpler than this one, or at least it looks like that to me. So I'm going to solve this one for ft and substitute it in here. Ft equals m1a plus fg1. And use that over here to say that fg2 sine theta minus m1a plus fg1, parentheses, equals m2a. And from this, a is the only thing I don't know, so I can start solving for a. So I'm going to take this equation and start to solve it for a. We write it out, we find fg2 sine theta minus fg1 equals m2a plus m1a. And then if I factor the a and divide by the sum of masses, I get a equals fg2 sine theta minus fg1 over m2 plus m1. And that is equal to, oops, sorry, sliding that up there. Fg2 would just be 130 newtons if I use my favorite approximation that g is about 10. So 130 newtons times sine 36 degrees from the ramp minus Fg1, 60 newtons, over the sum of the masses, 19 kilograms. When I do that out, I find that A is 0.86 meters per second squared. Again, that was fast. There are other videos on a very similar problem. If you want to go back and look at that, this is just putting a bunch of things together. Now that we have that acceleration, we can answer another question, or even another two questions. First, I wanted to know which way. Well, let's think about what I did. I had the tension force be positive, so this was positive. That means that when we got out a positive amount, this block went this way, up. If this block goes up, then this block M2 here is sliding down the ramp. So we could answer this block is going up, and this block is going down the ramp. We can also answer how far it goes down the ramp if we know the time that that takes. So we just found that the acceleration is 0.86 meters per second squared. Let's say that we let the block slide for 3 seconds. And I want to know how far down the ramp does that block slide. So delta x is what we want to find. And I can do, since there is only this acceleration causing it to move, delta x is 1/2 at squared, which would be 1/2 3 meters per second squared. Nope, sorry, getting ahead of myself. 0.86 meters per second squared times 3 seconds squared. If I do that out, I get it's about 3.9 meters. So the idea here is you can put together forces, trigonometry, and kinematics to answer a seemingly very complicated question in very simple steps.